Jacek Zurada, who is a Life Fellow IEEE member, serves as a professor with the Electrical and Computer Engineering Department at the University of Louisville, Kentucky. He has published 410 journals and conference papers in the areas of neural networks, deep learning, computational intelligence, data mining, and image processing. Co-authored 3 books, and co-edited a number of volumes. His work has been cited more than 12,200 times. He is a nominee for the 2019 IEEE President election. Dr. Zurada has received a number of awards for distinction in research, teaching, and service from IEEE and other organizations. He holds the title of National Professor of Poland and is a member of the Polish Academy of Science, and he was a distinguished speaker at IEEE SMC, CAS, CIS societies. So, if you please.
Good morning. Thank you for the introduction. I am very pleased to be here. I will, of course, speak English to this international audience. And thank you for introducing me. My background is really both European and American. My whole professional career was in the United States. But I met a few international friends from Europe. What I wanted to say that the topic of the presentation today is not exactly in power and communication, but it is a hot topic in my area of research. And I hope it will be of interest to you, especially that we are all carried by this big wave of artificial intelligence / machine learning / neural network / deep learning. And while results of the in the area of applications are very spectacular, what we got from these very sophisticated tools now in 3rd or 4th generation, because it all started like 70 years ago, 80 years ago, about during World War II or right after, what we got spectacular results which are not exactly matched by social trust or recognition or any support that we would offer to these decisions that artificial intelligence, neural networks, and deep learning make. Why is that? Because while these machines can do wonderful decisions for us, there is no explanation on or interpretability or justification for the decisions they make. So my presentation goes into many details, technical details, because as these mappings become very complex and more complex, in fact, because we are challenging machine learning systems to do more and more, distinguish between, say, not 1,000 photographs, but 10 million photographs of people's faces. So as challenges grow, the explanation capability from of these systems is becoming lower and reduced. So I would like you to keep in mind that while I'm going to get bogged down in some technical details, you cannot do that research without these details. But we are looking for a big picture, also, I hope, in this presentation. So I will suppress some of the unneeded details, but would like to talk about a big picture. So the big picture is how to build social trust, explainability, and understanding from neural network that make very sophisticated and clever decisions for us in the context of deep learning. So we want to understand the models that neural networks develop for us. And I will use a very simple non-negative matrix factorization background, but I will spread our thinking to perceptron networks, classic neural networks, as well as autoencoder networks, and tell a few things about other sophisticated methods of getting more interpretability of these machines, of these decisions. I deliberately have suppressed results from many other experiments that we have published in 3 or 4 papers. These papers are listed at the very end of my presentation in the bibliography. So I wanted to show just that what could fit into a general frame of thinking. My partners are PhD students, other professors, postdocs, from Turkey, from Poland, from Nigeria, and from Tunisia, and from the US. So it's a really international team. So the basic issue that needs dissection, and it's very frustrating for many researchers, is that neural networks deliver decisions as black boxes. And while decisions are trusted, they are very hard to explain, because the mappings are convoluted, intransparent. Even take 2, 3 neurons together and you are going to get bogged down into, I don't know what they are doing because of these complex functions like 1 over something exponent to the negative scalar product. It's getting complicated. So what we can do about it? For about 20, 25 years, people started developing simpler methods, but simpler methods were not that accurate. For instance, decision trees are very explainable, explanatory, I would say. Classic AI approach, decision tree, explanatory, simple. You can find out what is the justification behind it, but neural networks, which give more a better granularity of decisions, are not as simple to explain. So we're going to go this path. I would like to tell you about sparse mapping, mapping using non-negative weights, and how we can build decisions through superposition that can be applied to many cases. At the root of my discussion today is the concept of basis functions. So we use basis function all the time, but in neural networks, our basis functions are different. And I would like to redefine, following what has been defined about 20 years ago, receptive fields or feature extractors for the purpose of better interpretation. And what I would like to stress is we need to do training with reasonable constraints, because constraint training will give us favor in another area, in another domain, perhaps explainability. And we'll use decompose and reconstruct method, while keeping in mind that we need to do accurate classification, accurate sorting, accurate clustering as well. So this slide is kind of at the foundation of the exploration capability. I took this slide from Andrew Ng's lecture, one of the pioneers from Stanford, from Singapore. So what this slide says is that if you look at that landscape image, natural image, and you try to process it with the first layer of neural network, under certain circumstances, this network in the first layer will learn limited number of basis functions that are in addition indicative of certain shapes that are present in this landscape. So, for instance, you can take a square from the natural landscape, and it turns out that this particular square can be reconstructed by 3 learned bases scaled with certain real coefficients. So this test square from this landscape is a weighted sum of this learned basis, this learned basis, and this learned basis, weighted with coefficients. So it's a compact and relatively simple reconstruction of any pixel. So in other words, with these learned bases, we can put together again the whole set of pictures. So I will give you one very simple example. We will not talk about principal component analysis or singular value decomposition, which are acknowledged, legitimate method of dealing with matrices like that, because principal component analysis is for different purpose. It retrieves positive and negative entries. I would like to skip that. Instead, I would like to talk for a minute about non-negative matrix factorization, because it's at the root of this discussion today. So, when you have two numbers, when you have a number 6, you can express it as a product of 2 times 3, for instance, or 1.5 times 4. Under certain circumstances, you can take a matrix and decompose it into a product. And if this matrix is non-negative, you can try to decompose it into W with non-negative entries and H with non-negative entries. So this process is called non-negative matrix decomposition. And how it works is that if you express a data vector as a column of the matrix A, let's say this, here I'm showing the 4th column of matrix A, which is called data matrix. So here we have, say, K columns in this. Now, we have M, this matrix is M by N. And we can choose the size of this matrix as far as number of columns is concerned, and decompose the whole data matrix into W times K, where these columns of the new matrix W are going to be basis functions for encoding the data matrix A, and these basis functions are multiplied times entries here that are called encoding coefficients. So this is a set of encoding coefficients for these 5 or 6 basis functions, and once you multiply this times this, plus this times this, plus you create 5 sums, you are going to restore this vector, the single data vector. So these serve as basis functions, and these are encoding coefficients. These are examples of various, this is a data matrix. This is a non-negative matrix factorization with 10 columns, with 6 columns, because you can choose the number of columns here. The more columns you choose, the more accurate is the representation. So non-negative matrix factorization is kind of a native, naive approach to expressing anything with basis functions. So in a way, we combine vectors that are produced through decomposition. The decomposition is totally numerical. So A equals W times H can be reached numerically in a pretty simple way. So there is a lot of advantages of this approach. We don't need orthogonality of bases. In fact, bases are not orthogonal. We have flexible factorization criteria. We can get very sparse basis functions, but there is accuracy is a problem with that representation. So in very serious applications, NMF takes a backseat, but it's very often used in recommendation systems, okay, where each rating or each user is represented as a data vector. So I would like to switch to neural networks now, which are kind of new generation of non-negative matrix factorization idea. And I will talk about perceptron networks and autoencoders to give you just a rounded picture and report about a few experiments. So the Perceptron network is the workhorse of neural networks. It is a multi-layer creature with here 2 layers plus an output layer that usually does a classification. These are input vectors. Weight matrices are W, bias vector is B. And a classic classifier with neural networks looks like this. I'm heading towards neural network that has non-negative weights, but I will show the general architecture first. So here is a digit 6 as written in the database MNIST, M-N-I-S-T. That is a very classic benchmark set for pattern recognition, consisting of 60,000 objects, all 10 digits. And this is a 28 by 28 bitmap. So you can process it and, let's say, apply so-called softmax neurons at the output. And softmax neurons have this very interesting property that they give you probability of a class. So here, for instance, if you show 6, probability of output being 6 will be the largest, should be the largest, okay? But this thing is to perform classification for 3 classes, okay? Normally, the number of classes is very large, but I don't want to talk about it because I'm looking at how we can make this network understandable. So softmax is a very unique creature that converts values between -1 and 1 to probabilities. And it is regularly trained through error backpropagation as the whole network that I've shown you. And I would like to start injecting our own work right now. So about 3 years ago, we published a paper that documented that you can make the entire Perceptron network, no matter how many layers it has, and it has softmax neurons as well. You can make this network with non-negative weights. And all the negative coefficients that have to be somewhere, you can push them into bias vector. Bias vector is kind of a dead vector because it doesn't even connect to input patterns, to the bitmap of 6. It has a fixed input of 1 or -1. So, in other words, we can make neural network with positive weights, period. And if you know that 6 can be composed of pieces, number 6, then it will be 1 plus 2 plus 3. And you can easily grasp 1 plus 2 plus 3, but you cannot grasp if 6 is a combination of positive and negative coefficients, because 6 can be also -6 plus 6 plus 6. So it's getting more difficult if we have negative numbers. So we are forcing and training to make our weights non-negative. This is a subset of MNIST digits. I just wanted to show you for the purpose of informing you what pictures have been used for training. And this is an example of a non-negative neural networks that we have been able to develop on these MNIST bitmaps. And these are unfortunately very small little bitmaps, but they are 28 by 28. They are kind of windows through which you look at the pattern that is at the input. So in other words, these are receptive filters, and there is 10 of them here for this example. There is weights and outputs recorded for that particular input. But what I wanted to perhaps show you what this network does for us is this. It recognizes digit 6, but it recognizes it in a very special way. Look at the back. Explainability can be traced from the back. The probability of 6, that 6 is input, is almost 1. Probability of 1 and 2 is almost 0. So this high value of probability is generated by high value of this decoding output. And this decoding output is because the positive weights that are marked as large squares, the other gray weights are 0, because the positive weights that are marked as 6 large squares are combining large inputs from here. So these are combiners of these inputs marked with dots, 1 and 4 and 5 and 8, 9, 10, as you can see here. It's a little bit abstract, but then so you can see that the 6 is a composition of this receptive field and this and this. So you combine 6 receptive fields to get the probability of close to 1 of 6. So this was kind of a remarkable observation. Now remember, you are dealing with a very complex picture of 724 pixels. If you had a pretty simple thing to recognize, the receptive fields would be simple, and this decoding map would be simple. I mean, this wouldn't change anyway. But so that's the idea that I wanted to show you, how you combine positive weights, positive receptive fields, and everywhere except for biases which are negative, you can build a recognizer. Okay. You can do the same thing with Autoencoder. I would like to introduce Autoencoder a little bit later. And here is a counter example. For instance, if you recognize digits 1, 2, and 6 with unconstrained network that has positive and negative weights, you are getting all kind of addition and subtraction. Eventually, you are going to do the same recognition, but now you are adding and subtracting contributions from receptive fields. And the receptive fields are also have positive and negative entries. So this is unconstrained network with positive and negative weights. Positive are white, negative is black, 0 is gray. That's how we do it. And here, an optimistic outcome that we have published in TNN, transactions on neural networks, that you only have weights that are positive or 0. Now, to say it, to show it, it's simpler than to train it. In order to train it, you have to build a sophisticated function that permits the recognition of all digits, but also puts constraints, eliminates negative weights. And we need to promote small weights. And so this is, I don't want to go into details. You need to discriminate class and promote small weights and promote sparse weights as well. And here is a kind of bundle of examples. If you look at the same digits, 1, 2, 3, 4, and so on, non-negative neural networks gives you receptive fields, selective receptive fields that look like that. Classic error backpropagation network gives you positive and negative entries of receptive fields. Principal component is about the same, and non-negative matrix factorization gives you little dots that you can put together to reconstruct the digit 6 eventually, or identify a class, but the accuracy of NMF is the worst. So I'm using it as a historical reference. And because Bruno, who has encouraged me to attend this conference, has done research on text analysis. I wanted to show this particular example of text analysis that we have done with our non-negative Perceptron network. So if you have a document, you can identify topics of the document by analyzing the occurrence of words, certain words in the text. And we have tried to find the topic, and the topics are here: acquisition, ship, wheat, grain. This was a discussion about commerce or agricultural product or something. So with non-negative, neural network, we haven't been able to get a transparent insight into the process, but for network developed with non-negative weights, we can say, for instance, that it's marked in yellow, that the topic acquisition is composed of 3 keywords that are listed here, and listed here. Well, if you don't limit the weights to the positive values, then you have to look at presence and absence of certain words, which is extremely difficult. Try to find out something that is missing, okay? Because a negative coefficient means the word doesn't have to be there. So here we have kind of a superposition, mental superposition. For us, superposition, who are trained as electrical or computer engineers, superposition is a kind of canonical principle. So that is all kind of amounting to superposition. Now, I have to say that once you develop non-negative weights, you are losing accuracy, but not that much to discount the property that you can see how you can reconstruct a pattern from sub-patterns. So we are combining or adding non-negative parts to get interpretability. The price to pay is slight loss of accuracy. I am a little bit over my time. I will try to speed up through several slides that are too technical, because I think for technical details, you can always go to a paper, while the ideas, when you go home, the ideas are more important than technical details. Technical details, besides, take a lot of lab time, a lot of experiment times, and a lot of presentation time as well. So Perceptron is a classic thing that learns in a supervised way. So you have input and desired output or target. Now, with ascent of neural network learning, we started looking at autoencoders. And autoencoder is a very simple thing that develops features in an unsupervised way because it maps input vector into itself. It maps it one vector after another. It maps the whole set into identical set, one vector after another. And it develops receptive fields as well in the first layer. So here is the field of receptive fields. So each vector here that fans into this encoding neuron creates a similar receptive field to the perceptron network. But it's just developed in a different way because you don't have class output here. You have identical pattern that is at the input. But through repetitive training, you develop representation of receptive fields that best characterize the patterns in the family, like from 0 to 10. And so this is a notation, weights of the input layer, encoding layer. These are the coding weights. And these are estimates of inputs. We develop all these weights in matrices W1 and W2 by making input and output identical in sequence, okay? 60,000 patterns in MNIST database, for instance. And you need to minimize this loss. The quadratic error, the cost function, that's the primary target of training. The JE should be 0. You minimize it. And there is M pattern in the set. But if you want to develop autoencoder that has some explanation capability, you need to put other constraints. So the constraints will be develop non-negative weights, develop as few weights as possible, because the principle of, or Occam-Razor principle tells us, don't overdo in terms of size of the network, in terms of size, number of weights, keep them moderately small. So the true full objective function for training is not really JE. This minimizes the error, this provides a sparsity of the network, a lot of zeros for weights, a lot of absent weights, a lot of absent neurons as well. Absent, I mean deletable or scratchable, or those neurons that don't contribute to the recognition or to the mapping process. And this is a regularization term which ensures that weights are of small values. It's necessary for accurate mapping and good generalization. So by minimizing this term, we are pushing the weights to the origin. It's a very simple exercise. You push them to the origin in every learning step, because you are creating a paraboloid in highly dimensional space to and minimize the error function. Okay, and here is how we develop an accurate autoencoder, layer by layer. This is a classic thing. It's nothing new. So you develop first output layer of the autoencoder. You drop this layer. You train for another layer, and you build layer in sequence. It's called, the whole architecture is called stack autoencoder. Eventually, you put the autoencoder together and fine-tune it. Fine-tuning means already doing a job, because autoencoding is a trivial exercise. You map a vector into itself. It doesn't serve any purpose, because it doesn't discover anything. However, it discovers features that the patterns have in the whole ensemble. So if you wanted to hire autoencoder to do the same job as perceptron networks, which means classification of a written digit, handwritten digit, you use the layers that are mapping feature after feature after feature, and do with softmax neuron probabilities for you. But this is all differently generated. So our next step was to try to do explainable classification with autoencoders, and pursuing similar line of inquiry as we did with perceptron, we wanted the weights to be non-negative and sparse. So few weights and no subtraction. Subtraction, not a good performance. So what we try to do, we try to decompose data into parts that are sparse through the encoding layers, and combine parts in additive weight in the decoding layers. So the only modification that is needed now to develop, to get rid of negative weights, is to redefine the weight minimization term. Originally, just a second ago, I showed it as this one. But if we redefine the function f, and if we minimize this function, if a weight is positive across the network, it will not be touched. If a weight is negative, it will be pushed to 0. So that's the new objective function. So this is a learning with constraints that penalizes negative weights if they are any. Of course, 50% of weights statistically will be negative. We kick them out to the origin. We brutally suppress them, okay? So it is, in a way, unsupervised learning, and would like to show results. Without this weight suppression that are negative, you are getting positive, negative weights, black and white dots, and non-negative constrained autoencoder shows only white dots and gray, and NMF also white dots. So NMF is kind of a poor's man tool, and I'm using it as a reference. So at this point, because I'm a little bit over time, I started a few minutes late, so I thank you for the reminder, but I will bring a few points home. Eventually, you are trying to reconstruct the digits accurately. So these are reconstructed digits through processes in autoencoding. This is a separation of digits when compressed into 2 dimensions. Each color is a new digit, is a different digit. Of course, they are kind of touching each other. You cannot completely separate them because otherwise all digits would be perfectly separable, which doesn't happen. This is a special map that is very useful for this purpose. We compared all types of autoencoders with our non-negative autoencoders. The comparison was very favorable. We are not doing any worse than other autoencoders. Without comparing between existing autoencoders and your autoencoder, you cannot publish any paper. So that's the table of record that opens your entry or that legitimizes your results. So our NCAE, non-negative constrained autoencoder, doesn't do any worse than others. So we have been able to capture a part-based representation with autoencoders as well, not only with perceptron networks. I will glide through next generation of autoencoders. We have developed a more clever autoencoder because if you minimize a quadratic error, you only penalize very large weights. Small weights, because parabol is very flat at the bottom, in order to get better minimization, you add a magnitude L1, which is a linear function, modulus of x. But it has a trap because you cannot differentiate at 0. So we have devised special function. I don't want to go into it. We developed a similar autoencoder that did a good job as well. And these are experimental example. Again, this has been published in TNN. Now, to finish, I would like to show where are we going right now. And we have a paper in submission that is almost accepted. When we looked at these receptive fields, we found out that so many of them are similar or nearly identical. And so the idea was that we would aggregate them, cluster them. You can cluster anything, why not receptive fields? And by doing that, you are getting a smaller network and simpler network. And here is an indication that that particular receptive field is here, and it's in other 15 or 20 places. So you can compact the whole network by reducing the number of repetitive or correlated receptive fields. The algorithm that we have used was AGLO-SAE. It's a classic clustering algorithm. Here you can see this family of receptive fields. And taking this large map, you can compact this large map of receptive fields into smaller things. Now, why am I saying that? It is very difficult to express the complexity of handwritten digits. But if you have relatively simple data analysis task, you can really get good explanations from that kind of method. But I have not brought this to the conclusion in terms of simple business data or financial data or diagnostic data. Generally, pattern recognition, planar pattern recognition, digit photo recognition, or dog, cat, toy are complex problems, highly dimensional. So this is a comparison of classification results for our studies. And I would like to finish with that we've developed a set of techniques for data representation by compacting the filters, by making them non-negative entries. And we hope to have comparable classification accuracy in all these attempts and explanation capability that is much better than with positive and negative parts mixed together. In the references, I've listed a lot of things on slides 56, 7, 8. There's a few papers of us and a lot of papers of predecessors of us who started this deep learning explanation facility studies. The work on this topic continues. I know it's not exactly in the power and communication area, but I think that is one of the hottest topic. And if you look at the growth of conferences in this field, we suddenly have had 10 years ago, 1,000 people at a conference. Today we have 6,000 or 7,000, and billions of dollars investments into related fields of AI and machine learning. But one of the emphasis is how to interrogate the networks and get them explain something to us. Thank you very much.
Okay, thank you, Professor Zurada. For me, that was a nice class. I learned a lot today. Unfortunately, we don't have time for questions, so if somebody has a question, maybe at the coffee break, okay? Thank you.
Thank you.